Alright, now let's say we have, we're designing a motor or something, some machine, and we have the motor. So there's its shaft, and we need to attach a gear to it. Here's my gear. Oh, this is going to get worse before it gets better. Okay, yeah, gear, sure. And there's a hole in the gear, right? We need to get the gear onto the shaft. It's designed to clamp on really tightly, to be a really tight fit. In fact, the radius of the hole here is actually going to be smaller than the radius of the shaft. So let's say that the radius of the shaft is, I don't know, 1 centimeter, let's just go meters, 0.01 meters, and the radius of the hole is 0.009 meters. So how can we possibly fit this onto that? And the answer is we're going to use thermal expansion. If we heat up this gear, let me just zoom in on, forget the gears. So if we heat up this gear, the hole is actually going to expand while the entire thing expands using linear expansion. Okay, and it brings up a good point. And we know for the linear expansion of a rod or something, the change in length is equal to the initial length times the coefficient of linear expansion times the change in temperature. Well, it turns out that if you are heating up some material that has a hole in it, the hole expands with the same rule. So we can find the change in radius or diameter using the very same equation here. We use the alpha of the material that the hole is in. And it's a little bit interesting because it's not really the material itself that we're looking at. We're looking at a hole, but we can still use this equation. All right, so that said, let's figure out how hot we have to make this thing. Let's say that our normal temperature is just good old-fashioned room temperature, 20 degrees. Let's see how hot we have to make our gear before we can slide it on to there. Well, let's figure it out. So we know the initial temperature, we're looking for the final temperature. And I'm not going to plug in numbers anyways, but we'll say that we do know it's alpha. We know it's a coefficient of expansion. Well, in that case, let's see, we know alpha, we know the initial length is the radius, 0.009, right? And we know the initial temperature, not the final temperature, so we need to know the change in length too. Well, we do. We know that we are starting from 0.009, and we need to get it to 0.01, right? So it's the delta length is that difference, which is 0.001. Okay, so we just need to rearrange. Well, we need to do this first. So we'll go T final minus T initial, that. And rearranging to solve for T final, we should get that. So the final temperature will be this right here. So just another very simple simple example of using linear expansion here. Just keep in mind that if you've got a hole in a certain metal, it will expand based on that metal's alpha using the very same linear expansion equation.